Okay. Hello, everybody. Thank you for your patience. I'm having issues with my camera. So anyway, it doesn't matter for you all here, but if you are going to watch this later, you just won't be able to see me. But you'll be able to see the slides. You'll be able to see what we have on the screen. Okay. Any questions administratively? Yes, Paul. Yes, today. Today. Other questions? Okay, so we've gotten into a point of the semester where we're going to temporarily, this will be our last session on beams for a little bit. Okay, we're going to move into some other topics on pressure vessels and material properties, and stress, and strain, transformations, lots of fun stuff. And then we will come back to beams at the end. Okay? Because there's one critical thing that we haven't learned about beams yet. And the idea is, what do we know about axially loaded bars and torsionally loaded shafts that we don't know about beams? Yes. Superposition, okay. We will cover superposition and some, what else? Yes, Zach.
Statically determinate.
Okay, we haven't yet. Yes, we haven't. Yeah, that's true. We'll do that too.
Torsion on the beam.
Torsion on a beam. Now we're not going to. Well, we've done torsion, and you can superimpose that with beam. Yes. In the case, I'm sorry, I'm fishing improperly. We talked about stresses, right? In all three of these situations, right? We talked about bending stresses. Today we're going to talk about shear stresses and beams. Okay, we talked about forces. What have we talked about in bars and shafts that we haven't talked about in beams? Strain. Okay, we talked about strain a little bit, right, in this session, in number 13. We haven't connected strain to displacement, right? So we don't actually know how much these beams deflect. And so we're gonna hold that for a little while. Okay, we're gonna keep everyone in suspense, and then we'll get there. Okay. All right. So, what are we covering today in beams? We are going to spend some time, okay, discussing shear stress. Okay, so we're talking about transverse shear stress, okay? And then kind of for fun, you're going to see a couple topics that other people online will probably talk about as well, but maybe not in this context. I'm biased, of course, but I like how we've been doing this. Okay? And, so some of you have asked it to be more example-based, and some of you want it to be more theory-based. I feel like I can't win, okay? But that's okay. Today, there's some pretty good theory if you watch the videos. Okay, if you watch the videos, I think it doesn't. I go through some of the theory. Okay, we'll try to back out more to the application today. All right, so that you know how to do some of these things. And I do suggest, if you haven't started watching the videos, this is probably about the time where stuff is getting newer and newer and newer, and people start to be like, okay, I really should watch the videos. Okay, but to each their own. To each their own. Okay, so when I talk about shear, single shear and double shear, what I'm talking about is, say you have a bolt, okay, and I've got one plate pulling this direction, and I've got another plate pulling this direction, okay? Now, what may have been missing, okay, not that I would ever mess things up, all right, is that we talk about this very small gap, okay? I purposely put them far apart here, okay? This plate, the top plate, and the bottom plate, they're purposely far apart. But in the slides, what you'll see is that they're very close to each other, okay? Because when we talk about single shear, all right, what we're talking about is a situation where we're looking at a force, okay, being applied along the plane of interest, right? Along. So what is it? The plane would be there, right? And the force is parallel to it. So that's a shear force, right? That's not a normal force. It's a shear force. So in this case, in single shear, okay, what happens is we think about this cross-sectional area right here, okay? And that's some cross-sectional area A. And the shear force is going to be shear stress is going to be the force divided by that area. Okay? So if you're looking at this, if I took an element right in there, right? What would the element look like? It would look squashed. And it would look like it's being sheared like this. So this is F over A. This is actually F over A. This is F over A. And this is F over A. Okay? See that? Okay, and if I put some coordinate system, right, I could say, okay, that's this, you know, if I said this was Y and this was X, right, then I could say, well, on this face right here, that would be like my tau XY. Right? So this would be, okay? Any questions on that nomenclature? All right? Now, when we liken these situations, so double shear and single shear, to beams, what we are talking about is not the plates being the beam. What we're talking about is the bolt being the beam. Okay, so the beam, you know, again, if I kind of crudely, let's see, I think I can copy this. Okay. If I bring it down over here, okay, what I'm talking about is thinking about this as the length of a beam, okay? So what we're looking at essentially is a beam that might be fixed kind of like this on one side, and there's a force being applied on the other side, okay? And it has some length L. Now, if you want to be real particular, maybe it should be something where it's like a structure over here that restricts moment as well. Okay, so like it's some type of column that is having some force that's being pushed or pulled to the right. Okay, that's not how I treated it. Okay, but what we're talking about is we're beginning to think about beams, and we're beginning to think about the shear that could be inside the beam, right? We've talked about the bending moment, we've talked about the bending stress, and the bending moment and the bending stress. Well, bending stress is a normal stress, right? And bending moment contributes a normal stress. the shear, right, when we, back in statics, the good old days, right, we were drawing beams and we were saying, hey, look, you've got to have a shear force to make things balance out, right? Now we're saying, look, there's a shear force inside this beam. Okay, so let's think about that for a second. If I take this beam that I like, right, and we've seen before many times, when I break it down, does anyone know MC Hammer? Right? He would break it down, right? Okay, so if I take a slice here, right? If you don't know MC Hammer, talk to your parents. Actually, yeah, I guess some of them are old enough. Yeah, okay, or young enough. All right, so here we have V and we have internal moment M. Again, following the convention, right? Following the convention, so we've said in the past, if you're going this direction, okay, let's call this x2 because that's uncomfortable for us. We've said that, look, there's going to be some internal shear, okay, and that's going to be V, and that's going to be equal to P, right? And how does the shear change as we go from left to right or from right to left? Does it change? No, it doesn't, right? It stays completely constant. There's no distributed force acting on this beam, right? And there's nothing that we hit until we hit the wall, all right? So this shear force, in the shear force diagram, okay, and I'm not going to do the bending moment one right now. Right? But if this were x coming from this side, or maybe we'll call x1, okay, coming from the left. Okay, either way, this is just going to be P. Okay. So, that's like, you're like, okay, well, there's a shear force. Shouldn't there be a shear stress? Yeah, there is. Okay? There is. Okay? So, if you take a look at this beam, all right, what's happening? Okay, so now let's take a blow up. Okay, so this is that beam. All right. What we end up doing is we end up. Okay, how do I want to do? Maybe I don't want to do it this way. Let's do it this way. Let's do it this way. Yeah, let's do it this way. Okay, let's do it. Okay, can you kind of see that? That's the wall. This is the beam. All right? And we'll say we're coming out of here. X. All right? So the convention, if we now say this is like a slice. Okay, the convention is that we have V coming down. Right? And the convention is that we have a bending moment like that. You guys agree with me on that? That's the convention. If you take, right, if we're coming now, we're in X1. This is X1, right? Coming out of the wall, right? That's the convention. And this V is in the opposite direction of this V, but they're equal and opposite. Okay? So now, if I think about well, actually, let me just draw something else. Let me just put something else here. Look, there's a force acting on a face. What does that mean? That means that the average, okay, and that's where maybe something is a little, I'll get into this in a little bit. There's an average shear stress that we can draw, what we can think of as V over the cross-sectional area A. Okay? So, yes, there is a shear stress. Okay? Now, it turns out, and if you go through the derivations that are in the video, what you'll see is that it's not constant along that face. Okay? What actually is happening is on that face, okay, on that face where the neutral axis is, okay, the shear stress is a max here. Okay, and it's a minimum, and it's 0 at the top and the bottom. This is the exact opposite of what happens with bending stresses, right? Bending stresses, we have negative my over I, right? Here, we're going to introduce a new formula, which you can look at in the videos. Okay? Okay? Where it's, what you think of it as V quit. Okay? So this is very applied, high level, watch the videos, right? And then it goes through, we go through the derivation of this. Okay? What is V quit? This is the shear force. This is called first moment of doom. No, first moment of area. Okay? This, okay, is the second moment of area. And it's for the entire cross section. Please note, it's for the entire cross section. So typically that's VH cubed over 12, okay? For a rectangular cross section. T, this is also confusing, okay? Sometimes it's called height, sometimes it's called width, sometimes it's called thickness. Actually, no, it's not usually called height. Sometimes it's called width, sometimes it's called thickness, okay? This dimension T is in this direction, okay? It's into the board in this case, if you're up on these, on this two-dimensional drawing, okay? So this is thickness or width, but not height. All right, but I often say height. I often say thickness. I'm like, because at least when I think of bending moments, I'm thinking thickness is this direction. So you have to forgive me, okay? Please be understanding. This T is not that. It's the other one. Okay. So they didn't call H. Okay, Hibbler doesn't call it H for a reason. Okay, now, what is the first moment of area? This is, okay, so I is pretty self-explanatory. T is kind of explanatory. V is self-explanatory, right? Because we said, right, what we're going to do is the same thing we did with bending stresses, is first we figure out what the M is, and then we figure out what the bending stress is. Same thing here. First we got to figure out what the V is, then we can figure out what the shear stress is. So what is Q? All right, and there's a whole section on that. Okay, first moment, there's a whole video on there, okay? And I encourage you to read this, or read it. Watch the video, or at least listen to it, but preferably both, okay? This quantity can be given as That's super useful, right? Super useful. Then I'll give you another one that's really useful. Okay. You're like, wait, what? This is what happens when you just memorize equations. You have no idea what this stuff means. Okay? All right. So, when you watch the video, what you're going to see is me go through how to handle a cross-section of a beam and different shapes of beams, okay? And like you have hollow cross-sections, you have circular cross-sections, we have rectangular cross-sections, okay? Now it turns out a lot of this theory, V-quid doesn't work well in all cross-sectional shapes, okay? But it works pretty well for rectangular ones, and it works okay for hollow ones as well, or hollow rectangular, and it works okay for circular, okay? What you're going to be interested in, okay, is finding the shear stress at a particular location. Okay? And let's say that location is some y prime. Now the shear stress is the same along this y prime for our intents and purposes. Okay, you could argue it's different at the edges, okay? But for our intents and purposes, it's the same. It's constant across that width. See, I did it. Across that thickness. Oh, I did it again, right? Remember, T is this direction. Okay? So, just like we had my over I, right? And y is describing where you are above the neutral axis. Y prime is describing where you are above the neutral axis as well. What is interesting, okay, and this goes to the fundamentals. So let's say we have a beam that we cut. We have a beam, and now we're looking at you have no idea what we're looking at. All right. Let's do it this way. Okay. What's happening, okay, is remember we had a shear stress. We have a shear force acting on this surface, right? So we have some V. I'm going to delete it, right? We have some V acting on it, all right? And now we're trying to see how it varies as a function of y prime. And if we were to look sideways, okay, so if this were to be our dx element, okay, what you're going to see is that this is the neutral axis this direction, and this is dx in this direction, okay? What you would see is as you go y prime up in this direction, okay, is that there's going to be some shear stress that compensates for bending moment. Okay, so there's some like shear stresses, or there are some bending stresses coming out of this, and there's shear stress tau on this face. Okay? So and why does this work? It works because if I took an element, okay, so this is where it gets deep. If I take an element okay, this is just an element now. And I say that, look, I'm interested in a shear stress, tau, on this face, okay? Then there's got to be a shear stress acting on this face, right? And there's got to be a shear stress acting on that face, and there's got to be a shear stress acting on that face. Do you see what we just did? And now if we look at this element, Okay, we have shear stresses. You see this? This purple is this face. This is going behind the face. There's got to be a shear to keep this whole element in equilibrium. Questions on this? There must be questions on this. Yes?
Can we do an example problem?
We will do some examples. Okay, yes?
Could you just explain again what the purple and the green were?
Okay, so this is a beam coming out of a wall, right? The purple face, okay, maybe I should make it like this. The purple face, all right, is when I take a cut, okay, and I'm looking at it. If I took an element like right here, oops, wrong color. That face is this face, all right? But there's still material behind it. Okay, there's still material behind it. And that material behind it has to be having equilibrium, right? Otherwise that element's going to rotate. So there are shear stresses on the other three faces of this element that has one face on the wall, or on the that we've cut open, right? And what happens if you look along, and I'll just draw it this way. If you look along the element, or you look along the beam, sorry. If you look along the beam, and I take a slice of the beam, and that's what I have here, all green here, right? I've got bending stresses, but I also have a shear stress, okay, that's compensating for this. Okay, so that's just to paint the picture. What does this have to do with Q? Okay, well, if you look there, you can watch the video. There's a derivation for how Q comes up with tau. Remember, this is the equation. Tau equals VQ over IT. Okay, it ends up being very important to integrate, okay, the stresses and balance the forces in this scenario, and you get this equation where Q is equal to this. Okay, so let's talk about how you solve a problem. Okay, and let's go back to the problem we just had, right, where we had
Professor,
yes.
is it possible to actually solve it from A to Z and just plug in numbers?
I'm going to solve it in a way that I think will work for us right now. And then I encourage you to watch the video and solve the problems that you have, okay? So, here we have a beam with a shear force, right? We've solved this one a lot of times before, correct? So now, if I take a cross section here of this, okay, I have a shear force, okay, acting on a face of that. And it's constant, and we know it's equal to P, right? And let's say that's this slice right here, okay? That's this slice. Now, what we go ahead and we do is we say, I want to know the shear stress right in the middle. Okay? So right on the neutral axis. So I draw the neutral axis across it, okay? And I know that I have shear force, V, and I write out my equation, tau is equal to VQ over IT. Again. V, I know. V is equal to P. Done. I need to know T. T is this one. All right? So T. Done. I, well, if I know H, this height, we'll call it, I can figure out I. I is equal to, in this case, for this cross section, what is I equal to? Okay, so there's no B though, so what do I have to use instead? T, right? Okay, so once again, what's the one thing we don't know? We don't know Q. All right, so how do we go about solving Q? What we do is we say there's a y prime, okay, and then we go up to the location of interest. It turns out here y prime, though, is just equal to 0, okay? So y prime is the height above the neutral axis, okay? In this case, y prime is equal to 0. Okay. Now, we take the height above the neutral axis very seriously here. And we take the area above that height seriously too. Okay, so what happens is we say we're really interested in this region, just here. And we call this A prime. What is A prime equal to? You tell me right now. Yes, T times H over 2. Okay? Everyone see how he did that? He said, okay, well, it's only half the height, but it's still the same thickness. I'm going to redraw this again to make this try not to be so confusing. We take a look at that same region, and we find the centroid of it. Okay? Remember I said, hey, you don't understand what this equation means. Y bar, blah, 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 right? Now I'm going to define we're going to say that this is the centroid, okay, of A prime. Okay? So down here, what we're saying is that Q is equal to Y bar prime A prime. This right here is a centroid of A prime. And this is a simple shape. So where is the centroid of A prime? Of this. Where's the centroid? Yeah, right smack in the middle. Okay? And it's the y component. It's not the x component, right? The x component, it's the vertical component, not the horizontal component that we're interested in. Okay? So this is a centroid of A prime, and it's just the vertical component. Okay? And you can watch more video on this if you like. And Jeff Hansen has, I think, a video called What the Heck is Q? All right? If you want to watch that one, you can. All right? So this, as was pointed out, and I'm embarrassed, Jay, right? Yeah, Jay said it, right? What is this? This is going to be what? H over 4. Good. It's H over 4, right? Because this quantity right here is H over 2. Okay, and this quantity to where the centroid is H over 4. So Q is, again, y bar prime times A prime, and this is going to be H over 4 times, where was it, A prime? TH over 2. Okay, so now you plug in Q, you plug in V, which you know is P, I, which is TH cubed over 12, and T, which is the width. And that's how you that's how you calculate the shear stress. Now, that was just when y prime equals 0. What happens if y prime is not equal to 0? What if I say I want to know what it is at a distance of h over 4 above the neutral axis. What do I do there? What if y prime is equal to h over 4? And this is, this is not, let's say, harder question. Professor is still nice. Okay. All right, so here, there's a cross section, okay? And what we're saying is that there is a neutral axis, and we're saying that this has some height h, okay? And we're at some y prime, and that's equal to h over 4. Okay? This is the area of interest. So let's do that. And we still know that the shear stress at this location, okay, is still tau equals VQ over IT. So if V is equal to P, I is still equal to I, which is what we said was TH cubed over 12. This is a good reminder that I doesn't change as Y prime changes. It stays where it was. T doesn't change. T is still T. Right? Just check. So Q is the question mark. Well, we were told before that Q can be defined as y bar prime times a prime. Let's figure out a prime first. What is a prime in this case? Yes.
TH over 4.
Yes. Okay. Why is that? Because this is, we said we were at h over 4, so that means that's our h over 4 left, and it's still got a width of, or thickness of t. Okay. Now we got to find the centroid. That's the one that's kind of that's usually a little bit more painful, right? So there are multiple ways to do this.
H over A.
Excuse me?
H over A.
So so you did it faster than I can do it. So it's not h over 8 because it's the distance up, okay? So it's really this distance that we're interested in. It's y bar prime, okay, is the distance to the centroid from the neutral axis. So this is h over 4, and then this little quantity is h over 8. So it ends up being h over 4 plus h over 8, which is equal to 3h over 8. Okay? So then Q is 3h over 8 times th over 4, and I'm not quite sure what that comes out to be, 3 over 32. th squared. And that's how we go about figuring out shear stress. This is the primary way. I mean, I could make you solve the integral, and you should know how to solve the integral, okay? But typically, this is the process you're going to use. Okay, so make sure you know you go through the videos and you can solve. So I'll just say that. Make sure you can solve Q is equal to integral y dA prime over A prime. That's really messy. Okay, I can do better. Okay, any questions? All right, there was a request to go over problem number 3 on the last session, which I think is a valid request. So I'll do that real quick. And then I'll let you have some time to work on the problem set yourself. Okay, so here it is. Here it is. Okay, so in this problem, if you recall, what with the overhang, okay, what we're trying to do, and the reason this is already done is because someone came up, someone asked for it in office hours. Okay, so yes, you can look at the solution. In fact, let's just go ahead and maybe I'll pull that up real quick. Let's look at the solution real quick. Oh no, that's exam 1. That's exam 2, isn't it? Okay. All right. And I understand there's a screenshot of this 10 millimeters, which is not the same for everybody, right? There's an A, and I'm sorry, A is not equal to 10 millimeters for everybody. Okay. And you see these beautiful chicken scratch. Okay. And in this case, if you go through it, it is correct. What did I do? I did it the hard way. Okay? I did it going from the left to the right. Okay? But there's an easier way for the problem at hand. And the easier way is to go from right to left. Because it's saying we want to know what the bending moment is, what the bending stress is at a location some distance from the right. So what's beautiful is that you don't have to do all this. You can go about hitting this problem this way. And I'll just kind of redo it. I think so. I think that's the number. I can't keep track. So this is an overhang. Okay? And there is a distributed force on this overhang. Okay. No convention. Which way do I draw V? Up or down? Up, right? Because I'm opening to the left. Which way do I draw M? Smiley face. That's the easy one. Okay? This has some quantity, we'll call it W naught. Okay? And I think it's important that we understand what to do here. And you could have done this part from your time in statics, right? You did these types of problems. We're saying that we're some, now a lot of times in this case we're saying we're some distance d from the right. In our conventions, not conventions, but in future problems, you will see things where we say it's like x2. It's a coordinate system, all right? And it's coming from the right instead of going to the left. Not a big deal, all right? But we'll just leave it as d for now because that's what the problem's defined in. So in order to figure out m here, what do I need to do? What's that? Equilibrium. All right. That's right. Okay, so equilibrium. So what I'm going to do is I'm going to redraw this. And I'm going to say that there's an F effective. Right? That F effective is from the W naught. What is that F effective? Someone? Good. Okay. Where is it acting? At d over 2 it's acting, right? So it's acting at d over 2. So as d increases, right, this F effective actually moves, right? As I move along, what did I say? No, that's not what, I said it wrong. As I increase d, yeah, the F effective, its point of operation, its point of of contribution moves, right? And it's going to move d over 2 as well, okay? So now, if I want to do, like, I don't care, we don't care about this left half of the beam, right? We don't care about even this support, all right? It makes Bruno feel wanted, okay? So here we have M, which we'll say is negative. We'll say that our moment is also, from F, is also negative. Is there anything else? There's nothing else, okay? So the moment is just going to be minus W naught d squared over 2. And if we want to know the bending stress at a given location, right? So now we take a look. Take a look here, right? And we say, okay, we're at some location y, right, above, and so then we've got sigma is equal to negative my over I. And even before we do this, okay, we have some clue is if the point is above, if this is the neutral axis, if it's above that neutral axis, are those points going to be in compression or tension? Why in tension?
Because it's getting spread out.
Yeah, it's right. It's like, this is where you want to use the think methods, all right? You want to think about what is the deformation that's occurring. And that deformation, you get an intuition that that deformation, right? Even when I'm doing this, you're like, wait, that's negative moment you're putting on it. That's negative moment, or that's negative moment, right? Negative my over I. That means the top part is going to then be in tension and the bottom part is going to be in compression. I mean, if points are getting closer to each other, right, they're going in compression. I'm compressing it to get those points closer to each other. And if they're getting farther apart from each other, I have to pull them apart. That's tension. Okay? So even before we do that, we kind of have an idea that this location is going to give us a positive stress, a positive bending stress. So we've got I, which is a BH cubed over 12, right? And we've got Y, which is whatever it is, okay? And we have this M, so we have sigma is equal to negative, negative, so it's going to be positive, W naught d squared over 2 times Y over BH cubed over 12. This is going to end up being 6 W naught d squared Y over BH cubed. Did I do the math right? I'm not sure if I did the math right. Any questions? Okay. Yes, Kevin.
Could you go one more time where you're summing up the moments to derive the original equation?
Right here?
Yes.
This one?
Yes.
Okay. Good question. I need to pick a spot. I'm going to pick this spot because I don't want to be dealing with V. Right? So this is O, we'll call it. So the sum of the moments at O is equal to 0. Is that okay? Yeah, so it's really this distance that I'm interested in. That's d over 2 as well. Okay. Good. All right, so we've used a lot of our time, and it's fun. I think we will go ahead and put up the next thing. We're gonna do it at the end. Or what's the question? You have a question?
No. Can we just back them but I
No, we're gonna pass them out person by person after the class, or at the end in the last 10 minutes. You're gonna take half of them. You'll do it on this side. I'm gonna take half of them in the last 10 minutes because they don't like it when you just it'll chaos. Okay, please do not send me a message saying you missed the attendance.
Professor, why don't you keep it open for another hour till 8 and then it's easier to make sure that everything is.
I would like you all to spend the time in this class working to finish and work together, okay?
No, I'm saying about keeping the attendance open.
Because the class is over at 7. You're talking about the attendance? Class is over at 7.
I sent you an email.
No, okay, so this has come up a couple of times.
Yeah.
All right. And in the last 10 minutes of class, we'll return the exams. Uh-oh. If you're not done with the homework, then I think you should be here to work with other people. We're going to do it in the last 10 minutes. Yes.
Is there a class in here after this one?
I don't know. We've tried to reserve this room afterward, and we haven't been able to get this room.
Okay, I just want to know because I'm gonna watch the videos. I want to know if I have time to.
I think so, but we've tried to reserve it afterward, and it doesn't usually work.
Okay.
Yeah, we've tried. Thanks, Graham, for asking. So in Canvas, what you do, okay, is you.
I think we're tonight, so that you know, I'll
Okay,
just get the exam.
that's fine. See you, Jeffrey.
I'll get up there.
Yeah. Yeah, so you should be working on the homework that's due on Thursday. That's what I'm saying. We're here now. That's what I'm talking about. If you're done with the homework on Thursday, more power to you. Okay? This time is for working on that homework and asking your peers and asking Praj and me questions. That's what we're here for. Okay? That's what you're paying for, quite frankly. So you click on the inbox, and then once you click on inbox, you can come over here and hit compose.
Yeah, and then just put your name.
Yeah.
All right.
That's
okay.
it. That's
I'm
it.
gonna redo
That
it.
that way, because what happens is I get a lot of emails, and this way I know what's class related.
Okay. Yeah. Then I'm gonna screenshot. I think I can add it there.
Sure.
Right? Okay.
Sure.
Okay. I'll do
Yeah,
it.
but please, if you're in the class, please try to get it in before the end, because there's a lot of stuff now that's.
Oh, you want me to do it right now?
Yeah, for this class, of course.
Oh no, no for. I already did this class.
Oh,
attendance.
okay, for the previous.
I'm talking about the
Yeah,
previous
yeah,
class. I
yeah,
couldn't
yeah,
come.
that's fine.
All right.
That's fine.
Thank you.
Hey, Professor, I just wanted to say that I'm sorry that I'm not going to stay out here for homework.
Okay,
I
that's
don't
your
know
decision.
better.
That's your decision.
So I'll take it on Thursday, I guess.
Sure. At the end of the class.
And so regardless, I'm going to need to get on at 10 p.m.
Look, you're registered for a class that goes until 7.
I did not
They're
have a
helping me
choice.
out.
Yes, I have. I'm not gonna do it now because
No,
I
no,
want
no.
you guys to work.
Yeah. Okay, so regardless, I'm gonna need to take it on.
Thursday, yeah, or come to office hours on Friday, whatever. It's flexible.
They're helping me out. They're not. I need something. So
Okay, sure.
we just
Go.
finished. So we'll get it Thursday.
Yeah, that's fine.
There's not a
At the end of class. Because it's gonna, otherwise it's gonna be chaos.
And Professor, is there a feedback on the exam?
Is there a what?
Feedback on the exam. Feedback.
feedback.
So
Feedback.
you can learn from the
Feedback.
yeah.
Like, did you get like this is
Yeah.
why it's wrong and stuff like that?
Oh, I mean, yeah, you have a solution. You have, yeah, I don't know how much feedback you want, but there's points, there's just like,
You know, for the exam.
yeah, of course, you have the solution. Okay, so where's your location?
Spins pistons go up and down, sucks in air.
So this is 0.0028, is that, and this what is that? That looks right. I have it on. As long as you use it. I mean, again, the way I look at it, right, is I look at the V by doing a slice from the right. The V is just going to be, in this case, right, it's going to be F effective. Right, so if you're like at D over 2, right, it's whatever the F effective is. So F effective is W naught D, whatever that distance is. Right, so yeah, you can do it this way, but it's more, and it's great that you do it this way, but it's more prone to mistake. Right, because we just went through this.
Bro, that's good. This says 75. That's really good.
Right, so what we're saying is that the V, if I want it right here, the V is this F effective, W naught D, right? So whatever the W naught is, times that distance that you are. So it's 0.0034, right? And then what was the distributed force?
Negative 10,000.
Okay, so yeah, so then that's going to be 10,000 times that quantity. Which does look like it's right, because that's, what did you say, 0.0034? So the 0.0034 times 10,000 is that, so you're good. So the T that you're using should be this width, right? Yeah, because that's what A was given, right? So A is 0.1. It wasn't really 0.1?
So 0.01.
Yeah, 0.01. That makes more sense, right? Because it's, and that, did I specify? Because sometimes in the problem, we can take a look. Because I specified a slide length A, even though it says 10 millimeters here, it could be different.
And mine was
Yours was 10 millimeters? Okay, okay. Yeah. So then, yeah, I don't know why it wouldn't be right. This I, when you did it, you're using, again, A, which is point, right? Right, and then D is just T, right? Right. Yeah, we can see, I mean, because I mean, I haven't done all the calculations, but your process seems right. Alright, good, thanks. Hi, Judy. Yes.
So. Just make it outer shell and scale it up.
Yes, okay. Okay, so why,
Take a piece of paper.
why is 50 distance above the control
Okay, take that picture, take a piece of paper, trace it,
When
and
we
then
start
put it over your cat.
doing
And then
drawing,
yeah, that too. Trace over it, and then
is kind of just like why.
and then make it
Alright, why prime is going to use y prime is going to use the bottom of the A prime.
everything's
That's where we're going. That's we're not interested in the shear stress at the top, we're interested in the shear stress at y prime.
I have.
That's right. Yes. That's the most confusing one. Any questions? Any questions? Yes. Yeah. We should. The goal is not, the goal is to start working on this as soon as we have time. We've gotten into the thing where it's like, it's fun.
What's single shear, what's the equal to
Yeah.
One half.
this, right?
Yeah, one half.
So what is that?
Yeah, so, whether A equals to A was not,
Have it multiply this one.
sorry, what is the line?
Now, equation. And E is like behind C.
Oh, he is, bro.
Yeah.
I think you're at
Yeah, so that's what I was talking about. T is this width, and it's also, in this case, it's squared, but also. So you're telling me that I told you that okay, so I was confused on this one, but I'm gonna call it now, right? A prime plus what the also want here, right? And so, yeah, what's the midpoint is, right? So half of whatever that is, plus the distance y prime.
Oh, I did that like 2 years ago.
So you have, because just like you just moved here,
Just like we did here a second ago.
Okay. Alright. y prime is this quantity, right, for that dotted, that dashed orange line. Y bar prime is that to that. So what I often do is I look at, okay, I have a y prime, which is the h over 4, so whatever that is, and then I gotta add to it half the remaining height of a prime. Right, so I have whatever, so of this area, right, so I have to figure out, okay, what is, essentially I gotta figure out, this is h over 2 minus y prime, and it's half of that. H over 2 minus y prime is gonna give me this little sliver right here. The sliver between here and here. Okay. Right? What am I talking about? I'm talking about if I just define this little thing, that little red thing, let's call that, I don't know, let's call that C. That's not a proper thing. C is going to be equal to half the height, right? So that's going to give us, well, in this case, let's call this B, right? It's going to be equal to h over 2 minus B, right? That gives me this, all divided by 2. B is this height, which is h over 4 in this case, right? And so I got to figure out what, right? This distance here is h over 2, right? So to figure out what the height of this part is, it's that minus that, all right? So that's what this is, and then I got to divide it by 2, all right? And then y bar prime is going to be y prime plus c. Okay.
Yeah, I already had this part. I didn't.
Yeah. It's very common. Okay. Okay. All right, Praj, can you help me out?